we present a robotic construction system that is capable of building at the infrastructure scale, using highly heterogeneous building materials found on site. Our online system constructs free-form dry stone walls in heavily unstructured environments, using automatically detected and digitized boulders and debris, leveraging the use of a 12-ton autonomous walking excavator for mobile manipulation. We demonstrate our pipeline with the construction of 2 large-scale structures, built using over 1,000 unique elements with an average mass of 1 ton. The first structure is a freestanding, double-faced dry stone wall, measuring 10 meters long and 4 meters high, with an average thickness of 1.7 meters. Our second demonstrator is a permanent 65-meter-long retaining wall consisting of 938 unique elements that reaches heights up to 6 meters and is built with an unmodified mixture of reclaimed concrete, erratics unearthed in nearby construction sites, and locally quarried boulders. This retaining wall was built in the context of a public park and is integrated with landscape features that enable pedestrian circulation, water management, and erosion control. To facilitate the precision grading of these features, we also equipped the excavator with a grading bucket, using force torque-defined digging trajectories to precisely excavate in heterogeneous soil conditions. A continuously updating LiDAR map is used for online planning, ensuring that the excavation process continues adaptively until specified tolerances are met. We autonomously excavate 665 square meters of precisely rippled terrace surfaces with an active soil removal rate of 4.3 minutes per cubic meter. This work presents the first full-scale robotic assembly of permanent and performative dry stone walls, and is the first to showcase the potential of an automated construction platform to combine infrastructure-scale building and landscaping tasks on a single site. This high degree of autonomy in robotic construction is made possible by our developments in mapping, segmentation, grasping, and geometric planning, allowing the system to locate, manipulate, plan, and assemble irregular objects in the wild. Our mapping pipeline builds a volumetric model of the environment while identifying individual stone instances within it. We train the system on a dataset of randomly generated and automatically segmented stone piles by aggregating textured models in a physics simulation environment. The simulated data is supplemented with a small set of manually labeled real-world photographs of stones and demolition debris. Using the trained model, the system isolates individual stones in images collected by a cabin-mounted RGB camera, and these stone instances are propagated onto the accumulated 3D LiDAR map using a graph-based label diffusion approach to enforce consistent boundaries between objects. The segmented stone clouds are fed into the grass planner, which identifies and ranks grasp hypotheses, classifying them for force closure validity while avoiding collisions with the remaining points in the base map. Planned grasps are autonomously executed, and a full, detailed 3D model of each stone is obtained by in-hand scanning. Using the cabin-mounted LiDAR, we accumulate points on the stone's surface, relying on the known kinematic state of the excavator to filter out self-seen points on the excavator's gripper. These accumulated points are then meshed using Poisson reconstruction. The resultant mesh is then used to compute the stone's volume and mass properties to provide an intrinsic reference frame for future stone manipulation. During scanning, we also accumulate RGB images and use these to produce a sparse 3D reconstruction with its own camera pose estimates. The reconstructed point cloud is then georegistered with the LiDAR-produced mesh to provide refined camera poses for each image. The mass stone images are then reprojected onto the mesh to provide a textured model. We also generate a downsampled copy of the mesh that is used to compute geometric properties such as metafaces, edges, local reference frames, and feature descriptors. Each scanned stone is then returned to the ground and released. We account for settling by building an updated LiDAR map in the vicinity of the stone, and then using this map to refine the stone pose by ICP registration. In this manner, our geometric planner accumulates a limited inventory of fully digitized stones that can be used for construction. The geometric planner works to find feasible stone poses that are well aligned to an arbitrary mesh bounding surface specified by a designer. Using the known poses of previously placed stones, we create a simulated scan of the existing context by casting rays from a polyline centered above the in-progress wall. We reconstruct an approximated copy of the upper surface to define a closed search volume, and to produce reference frames along the wall's upper perimeter edge. We identify corners and joints along this perimeter, and use the low-lying set of points near these features to seed candidate placements. Stones from the inventory are positioned using fast geometric correspondences and are gradually refined towards stable and geometrically aligned solutions using a combination of torque and penetration-constrained ICP registration and physics simulation. These candidate solutions are further reduced using a supervised classifier built on a dataset of candidate poses from automatically generated walls with randomized bounding geometries. The classifier takes a 3-channel sign distance field as input, encapsulating solutions within an offset and voxelized bounding box, whose channels describe the stone geometry, the existing context, and the desired wall geometry. To place these candidate solutions, we once again leverage our grass planning pipeline, this time augmenting the LiDAR map with points populated on the known mesh geometry, and extending collision constraints to both ends of the pick-and-place sequence. After executing a grasp, we refine the pose of the known stone to account for shifting in the gripper, registering the mesh to a point cloud that is accumulated in the gripper frame while transferring to the placement location. The placement trajectory is then replanned using this refined pose, and the stone is placed using a linear motion that is oriented to avoid collisions with the existing context. The poses of placed stones are also refined using the LiDAR map, allowing us to account for any settling that occurs during placement. As many stones must be placed with specific orientations in areas with tight collision constraints, we design an approach to reorient and re-grasp arbitrarily shaped objects by finding an intermediate settled pose using a physics simulation, enabling almost any commanded stone pose to be placed autonomously, either directly or after an intermediate flip and re-grasp. Our robotic process allows for the assembly of large-scale walls using unmodified stones and demolition debris, establishing new possibilities for sustainable construction. We demonstrate placement rates of up to 5 stones per hour, approaching the speed of human operators. Unlike traditional methods, our system is capable of building complex, curvilinear surfaces without reference markers, and does not require a skilled operator, external guidance, or small wedging stones. The system also provides a full digital twin of the built structure for better accountability and future reuse. These large-scale projects allowed us to highlight the environmental benefits of the process. We performed the first carbon assessment for robotic stone construction, demonstrating that our method can reduce emissions by upwards of 40% when compared to an equivalently performing concrete structure. By enabling large-scale, autonomous construction with highly heterogeneous, low-cost, and low-energy materials, we showcase the potential of heavy robotic construction vehicles to increase the safety, efficiency, and expressiveness of construction projects, while simultaneously creating new opportunities for sustainable building and responsible reuse.